Excellent. Cool. Let's get started. How's everyone doing? Semester is coming to an end slowly, I guess. Who's submitting CVPR papers? You're submitting a CVPR paper. Nice. I'm also submitting a CVPR paper. So I have an interest in keeping this lecture short. Unfortunately, we have a topic that I find very fascinating, and I'm not sure if we'll succeed at keeping it short. So this is a graduate level seminar, right? Which means that I get to talk about things that are a little bit more explorative in nature. So this topic is a topic that I include in this lecture, even though the impact of geometric deep learning on like 3D scene representations hasn't been big so far. But I anticipate it will be big in the future, which is why we talk about it. And there are by now actually a few examples of this kind of stuff. But this is in a way more educational than it is. So this is more of a, if you wish, like a study of methods that are useful to understand if you want to understand, you know, how 3D perception works, because it's kind of involved. So this is a little bit dense, this topic, and I have gotten into it, but this is not something I am like the world expert on. So please bear with me and like ask questions and let's discuss. Cool. So the topic is geometric deep learning. Brief refresher, where are we? Right. Of course, this is, again, the old framework that we came back to. We say we want to solve the topic of neural scene representation, which basically means we want to go from images on your retina that are generated by 3D scenes to the representations that you have in your head as you walk around through the world, right? So like when I'm walking around here, I have a representation in my head that makes me not run into these chairs. Excellent. There is a question of inference. How do we go from images to 3D scene representations? And that's what gave this lecture the name, inverse graphics. And in fact, the inference part is the part that we are talking about today, and we're really zooming in on one particular technical aspect of this question of inference. Okay. So this is done. Wait, I'm confused. Ah, yeah, there we go. So, yeah, this is a refresher, sorry. I'm now confused. Is this the right slide deck? Apparently, okay, good. Okay, today, geometric deep learning. We're zooming in on inference, exactly. So, what is geometric? Who knows what geometric deep learning is? Nobody. Fantastic. So that's actually perfect. This is then the reason for this lecture, so that you'll all have heard about it today, and you'll learn a little bit thing. So what's the idea of geometric deep learning? The idea of geometric deep learning is basically that the 3D world is impacted by certain transformations. We already talked about one class of transformations, which is camera transformations, right? Like the images that you capture are a function of like the camera transform. That is like, okay. So what happens to the image as the camera moves around? We already discussed this on the level of like image formation and on the level of camera transformations, right? We said like, oh, if I give you a 3D point cloud and I give you the parameters of some camera, then you can predict what the image might look like because you can project the point cloud onto the image and do all of this rendering shenanigans, right? But then the problem is kind of that the kinds of algorithms that we use to go the inverse direction, so to do inference, right? These algorithms have to have a particular property. Let me give you an example. If I show you this bottle, and I show it to you for the first time, right now you've never seen it before. Unfortunately, you've seen it many times before. But now you imagine you see it for the first time, and then I hide it. I turn it away, and I like walk away, and I pop out back here, and I show it to you again. You know it's the same bottle, right? But the image on your retina has changed dramatically. In particular, the bottle has gotten a lot smaller. And yet your brain has zero problems at recognizing that this is the same bottle. And so your brain has, with respect to the identity of this object, a property that we call scale invariance, at least. Your brain is invariant to the scale of the object as it appears on your retina, which allows you to recognize objects constantly and to never lose track of them. And if you look at this room, actually, this is a particular striking example, because as I look at this room, right, we have all of these chairs, and I I very easily put all of these chairs in like an equivalence class, which says basically all of these are the same chair. Even though the image that I get on my retina for each of these chairs is very different. They all have different scales. There's perspective distortion and all of this stuff going on. And the idea of geometric deep learning is to say we have transformations that act on our data. In this case, the transformations are things like the 3D position, rotations, perspective transformations. And we want to build neural networks that are invariant to these transformations, or that are equivariant, which we're going to discuss in a moment. Okay. Has someone heard about this idea before, like invariance, equivariance? A few people. Good. Cool. Let's get into it. So many of the slides are from this guy. If you want to have a, like, this person here has a perfect, really amazing write-up on if you ever want to get into this topic. I think this is the most accessible write-up on group convolutions. It's basically the lecture notes of his class at the university that he's teaching. So if you want to get into this topic deeper, or you are confronted with papers that talk about this kind of stuff, and you're lacking the mathematical basics, this is the stuff to read up on. Cool. Let's get into it. So here's a funny little experiment like I gave you this like very practical experiment of like what happens to the bottle, and you have to be invariant to scale and whatnot. But there's actually one experiment that you're all very familiar with. Let's say I wanted you to build a image segmentation network, and this image segmentation neural network takes the image on the left and it predicts the image on the right. So it takes an image of a cat, and you want it to predict the segmentation mask on the right. What neural network would you use if I asked you to do that? Like classic image processing tasks. Okay, so your choices are recurrent neural networks, fully connected neural networks, convolutional neural networks. What do you use? Good. Okay. So you would be using a convolutional neural network. And what would the convolutional neural network do? It would take the image on the left, and then you all know how a convolutional neural network works. It has this bank of filters, and each of them filters the image, and then in the end, you can make it such that it predicts like n, for instance, probabilities for n classes for every pixel, right? So this would be an example of a fully convolutional neural network. Great. But the question I'd like to ask you is why? Why do you use a convolutional neural network? Why not take the image, flatten it into a big vector, and stuff it into a fully connected neural network? And then train a fully connected neural network to make predictions for every pixel. Yeah.
I think the convolutional network can sense the neighborhood of a pixel, and that's very important for a segmentation task.
Right. So there's a notion of locality. So there's so fun fact: any function that you can implement with a convolutional neural network, you can also implement with a fully connected neural network. Right. So this network can also reason about neighborhoods of features and pixel size. It's like this thing has the same input, right? It can also reason about what pixels are next to each other and what pixels aren't next to each other. But your answer goes in the right direction. So clearly there's something that feels different about the two, right? And you are right that there is a notion of locality that is in convolutional neural networks. Okay, so locality seems to be one reason. So why, let me ask this question differently. Why is this a bad idea? Why would you not do this in practice? For the record, no one does this, right? So. And it's worth to reflect on this a little bit. Why is this not something that people do? Right? So maybe sometimes you hear the story about people are like, oh, why are vision transformers so good? And people are like, vision transformers are great. Vision transformers are way better than convolutional neural networks. And then, empirically, this appears to be true. You can train vision transformers, and they do better on some benchmarks than conv nets. But why? Why is that the case? And then if you dig a little bit deeper, people might tell you, oh, they have convolutional neural networks, they have this rigid framework. They do something in a very specific way. They have all the structure built into the network. Vision transformers have way less structure, so they can learn the rules. All of this is complete hand wavy, right? The people are like, oh, they can learn the rules by which to best process images, and therefore they're better. Okay, maybe. But what's the neural network that has the least amount of structure? It's a fully connected neural network. So if all of that were true, why don't we just if scale was the answer to everything, why wouldn't we just take all the images, flatten them into big vectors, and stuff them through a fully connected neural network, and then we train a huge fully connected neural network on all the data we have? That would clearly solve all of our problems, right? And to be fair, I don't think anyone has tried. So I'm not saying that's not feasible, but my guess would be it wouldn't work that well, in fact. So why is that? Okay. So here's a specific example why this fully connected neural network is a bad idea, and why you should absolutely not do that if you want to process images. What happens if you train like what happens to the output of the fully connected neural network when you take the cat and you shift it. Yeah. Right. So, yeah, it's kind of a. I'm now realizing this is kind of a stupid question. I should ask the question the other way around. But like the thing is, you don't know what happens. You literally don't know. And so your answer is exactly right. So the thing is that. So let's say we want to do semantic segmentation, right? The task of semantic segmentation. Let me go. Let me see what comes next. So the task of semantic segmentation has a specific structure. The task of semantic segmentation in image space has the structure that when I take the thing that I want to segment and I move it in the image plane, the semantic segmentation mask moves accordingly, right? Like the semantic class of the cat is like doesn't change when you move it around in the image. Clearly, that is true. So the fully connected neural network doesn't know that. When you take the cat and you move the cat in the image plane, the fully connected neural network, you don't know what it's going to do. It like from the perspective of the fully connected neural network, these two images are completely different. They're completely different. But we have this idea that the structure of the task is such that when we move the cat in the image, the task, like the segmentation mask, moves by the same amount. And this is a property we call shift equivariance. And we're going to formalize this in a little bit. But the property that this property is called shift equivariance, which basically is just a fancy word for exactly this property, that if you shift the input of the thing, then the output should also shift. Okay, so convolutional neural networks, you might use convolutional neural networks, or convolutional neural networks are one reason why convolutional neural networks are very good at processing images is because they are, by design, shift equivariant. So here's an example. If you take this image on the left, and you input it to a convolutional neural network, and then you move the image around, then the output of the convolutional neural network will move around like that as well. Different from a fully connected neural network. If you do this with a fully connected neural network, it'll be like a whole disaster. Okay. However, clearly, so this is an important property, and it's good. However, as we just discussed, and now, just to be perfectly clear, we're now entering domains of things that people don't know how to do. Like the simple example that I just gave you with like moving this bottle back and forth, we said that is an example of scale equivariance, like or scale invariance. You want to be just like the cat doesn't change its character when you move it in the image plane, this bottle doesn't change its character as it gets smaller and bigger on your retina, right? So there clearly are other kinds of transformations other than shift that we would like to be invariant or equivariant to. And one good example is rotations. So convolutional neural networks, oh man, I can't interrupt this animation apparently. Okay. So clearly translations are good, but what happens to the output of a convolutional neural network when you rotate the image? So here, for instance, is a satellite image, or it's like a image of a fisheye map. If I take an image and I rotate it, then the output of the convolutional neural network is not equivariant to rotations. What does that mean? So like here on the left, you see an image rotating. Here you see the output of a convolutional neural network, and here you see like the output stabilized. So we like now just canonically oriented, so we keep it kind of fixed. And you can see that as the image rotates, the predictions of the convolutional neural network change, right? Although if you're like, I don't know what this is, like imagine this was a semantic segmentation map, right? Then the semantic segmentation would wobble around just in the same way. And if that happens, right, then you're unhappy. Let me give you another practical example of this. Like if you do a headstand, then you can still recognize this room just fine. Or if I take like my laptop and I rotate it, you can still notice it as a laptop, right? Your prediction of the fact that this is a laptop doesn't change as I rotate it. But your convolutional neural network struggles with this. Bad news there. Okay. Now, the interesting thing is that there are, just like there are convolutional neural networks that are shift invariant or shift equivariant, we can build convolutional neural networks that are also rotation equivariant. And these are called group equivariant convolutional neural networks. And what happens in this case, you can see here. So in this case, same exact thing. We're rotating this image. This is the output of a group equivariant neural network, of like a rotation equivariant convolutional neural network. And you can see that when you stabilize the output is almost perfectly still. The reason why it still wiggles around a little bit is like stuff like aliasing. So like when you're rotating the image, like you're interpolating the pixels, so it still wiggles around. But if the image was like super high resolution and you did everything right with anti-aliasing, the image would be perfectly fixed. Any questions so far? Great. Then let's get into how we're going to do it. Yeah, symmetries in nature is another thing. Like we already talked about this, but basically symmetries appear to be like a very important thing. Like in nature, you can certainly see them a lot, right? Like so this property is actually so this property that we just discussed are often called symmetries of the problem. So shift equivariance is a symmetry of the problem. Let me briefly tell you why people call this a symmetry. They call it a symmetry because under a certain transformation, a property remains unchanged. So under a translation of the input image, there's a property that remains unchanged up to translation. And symmetries in the normal world, right, when you refer to the symmetry of an object, usually you mean there's a mirror symmetry. But that's basically the same idea. Mirror symmetry means that there's a property that remains unchanged under mirroring. So if an object is, when you say an object is symmetric, then you usually mean that there is a property that remains unchanged under mirroring, which is like the 3D shape. Okay, so that's where like why people call these two things symmetries. And nature has many such symmetries. Like you can find them in proteins, you can find them in like leaves, you can find them in humans, right? Most humans are approximately mirror symmetric. And there's many reasons for why that might appear. One of the reasons sometimes is mentioned that symmetries enable you to put like lots of information into, like it's kind of a form of compression. So for instance, if you want to store the way in which you want to arrange leaves in like a succulent, so here's a little succulent, this is, if you want to, in the DNA of this plant, encode how to arrange the leaves such that you maximize the amount of light that they get or something like that, then storing the position of each leaf separately in the DNA might be very costly. But if you just like identify like some symmetry of the problem, you're saying, okay, like you find the rule, you encode the rule in the DNA instead of just by which the leaf positions are determined instead of just the leaf positions themselves, then you store, then you basically save on memory, so to speak. So this is like a theory. But more generally, like basically you could say some people have gone as far as saying that physics is the study of symmetries, like in the real world. So, and there's like, yeah, one can go rather far. But today we're just scratching the surface of like what is the relevance of this to machine learning and to 3D perception. Okay, so now we're going to introduce a bunch of boring terminology. And I hope you will stick with me, but it's rather helpful because these days this is a very hot topic in machine learning. So I'm sure you'll notice, you'll find papers that mention this kind of stuff. So in any case, this will not be wasted effort, I promise you. And it's actually also not that complicated. I must also say that the people that have like formalized this field, I think have done the community a little bit of a disservice because they really went a little bit overboard with like with the degree at which they're like pushing formalism here. But many of these ideas are the mathematical foundations that this whole area of geometric deep learning is built upon is like one of the best, like one of the most well-researched areas of mathematics. Like group and representation theory is like really old in mathematics and like really well documented. But that also unfortunately means that like the notation and the formalism has converged like to like a very, very, it's like the epitome of like abstract notation, basically, you would say. Okay. All of this to say, what is a group? So we're going to first introduce the notion of a group. So a group is actually just a set. It's a set of with elements G. It has a group product. And a group is just a set that has the following properties. One is closure, which means that if you have a group, so a group is just a set of like imagine like vectors or something, and there is like a group product defined, which is like a binary operation that takes two elements of the set and produces another element. Closure means that if you take two group elements and you multiply them together, the output of that stays in the group. So let me give you an example. If you take two rotation matrices and you multiply them together, then what do you get? Another rotation matrix. That's rotation matrices are like rotations are one example of a group. Another one is associativity. So if you take, well, self-explanatory. If you have three elements of a group, G, H, I, then then you can factorize it like that. There exists an identity element, which basically just means that if you take a rotation matrix, for instance, there's the identity matrix. The identity matrix is the identity element of the group of rotation matrices, right? And there's an inverse element, which basically always means there has to be a way of inverting a given transformation. So you can rotate something this way, and then you can invert it by finding the inverse rotation matrix, right? So these are the properties of a group. Let's go through a few examples. And now I think this is maybe the first thing that is useful, because you all know a bunch of examples of groups, but usually people don't think about translations, people usually don't formalize convolutional neural networks in this way, but it's rather helpful. One very simple group is the translation group. The group of translations has as elements these little vectors. Like, for instance, in 2D, the translation group has as elements two-dimensional vectors. There is a group product, which is a little bit unintuitive, but the group product ends up being addition of vectors. So if you take a two-element vector and you want to translate it, what you do, you sum it with another two-element vector, right? So you take something and you translate it. And the inverse element, of course, is just the same vector, just negative. Does that make sense? Okay, and so this should be intuitive. So each of these points is therefore an element of a group, right? So we are in R2. The identity element is the origin. So if you shift something by the origin, it remains unchanged. Any of these points is a group element. If you take a group element and you apply the group element to every other element of the group, then you basically just translate the elements of the groups. So far, so good? Excellent. Good. Next. So this is obviously the thing that appears to play some role in CNNs, right? Good. Then there's the roto translation group. So roto translations are, we talked about camera transformations, right? So this is this is where camera translation comes from. In 2D, roto translations are called SE2, special Euclidean group 2, in 2 dimensions. And in 3D, it's SE3. So SE3 is the camera matrices. And SE3 is actually made up of 2 subgroups. One is the group of rotations, and one is the group of translations. So the group of translations we just discussed, that's always if you take a camera matrix, right, there's always the translation vector. That's an element of the translation group. And then there's always the rotation matrix. That's an element of the rotation group. And so group elements of the group SE2 are therefore elements that always are signified by the rotation and the translation part. So every group element in the rotation group is actually made up of a tuple, a translation, and a rotation. And then, of course, again, there's the inverse, right? Like for any roto translation, you can find the inverse that basically takes it back to the identity. And now, if you look at the group, this might be elements of the group. So each of these is now a vector, is a point, like a translation and a direction, which is basically the rotation matrix. And now if you take a group element and you apply the group element to all of the other members of the group, now you're rotating and you're translating at the same time. Okay, so this is all just basically putting things that you already know into the language of group theory. Any questions so far? Good. Now, this you already know, but this is maybe something that is good to, this is like something where it starts to get a little bit unintuitive. And again, this is just so far introducing like notation, like how do people talk about these things? And all of these formalizations do make sense. It's just kind of stuff you have to get over in the beginning. It seems a little bit pointless in the beginning. So people differentiate between the so-called matrix representation of a group and elements of the group. Let me give you an example of what that means. So every group has a matrix representation. So for instance, for SE2, we already said SE2 is represented by these matrices here. It has the translation vector on the right, and then it has the rotation matrix on the top left, and then it has the 0, 0, 1. So this is the matrix representation of the group SE2. But the group SE2 are not these matrices. Instead, you can identify any element of the group SE2 in other ways. For instance, you can say, well, an element of SE2 is actually just 3 numbers, right? It's like 2 numbers for the translation, and then it's 1 number for the 1D rotation, right? So the matrix is not the group. We say that the matrix is a representation, like every group has a matrix representation. And it is worth noting that the identity element and the inverse element are, they always have representation, like they always have, I don't want to use the word representation. You can always find them both in like the kind of the, in the group elements as well as in the matrix representation. So in the matrix representation, it's going to be the inverse matrix, duh. But in the group, in the group representation, for instance, right? What is the identity element? The identity element is translation 0, and then angle 0. So it's actually just 3 numbers, which are all 0, for instance. And then the inverse element, if I give you this tuple of 3 numbers, 2 of which are the translation, 1 of which is the rotation angle, then it's just negative of the translation and like rotate the negative angle. Okay, then there's like the scale group, right? So you can scale and translate. So there's basically all these different groups. And for each of the groups, importantly, you can always find a matrix representation. So any group always has a matrix representation. All of these matrices are always invertible. And they do have to be invertible, right? Because for every group element, there has to be an inverse element. And that always has to be the inverse of the matrix. Duh. Okay, so now we have all of this new vocabulary. How can we use this to actually build convolutional neural networks now? Or how can we use this to build neural networks that are invariant or equivariant, or what does it even mean? That basically know about the structure of these groups. So the first, unfortunately, we still need to introduce a little bit more notation. The first thing to differentiate between is that there are group elements. So far, for instance, we looked at these points in 2D as each of these points was a group element, and then there's functions on top of groups. So this is just a set of group elements, and then there's a function on top of the space R2. So for instance, images are functions on top of R2, right? Does that make sense? So, and we say we will denote functions via this L2, like via this L notation. So, and this here just means that K is a function on R2. Great. And now there's a funny little thing. So if you have an element of a group, like for instance a point is an element of the translation group, then that element of the translation group is transformed by other elements of the translation group by the group product, which in the case of translations is just the sum, as we discussed. But for functions on top of this space, it looks differently. So if you have an image and you want to mathematically describe how that image is transformed by the translation group, then we will introduce a little bit more notation, just for the fun of it. So basically, groups are separate from the functions, like groups are separate from this vector space that they act on. So for instance, if you have the group of translations, then the elements of the group of translations happen to be 2-dimensional vectors. And 2-dimensional vectors are also just elements of R2. But for instance, if you look at rotation matrices, right? Rotation matrices act on 2-dimensional vectors as well. Like you can have a 2-dimensional vector in R2, and you can rotate it. But rotation matrices aren't themselves 2-dimensional vectors. So generally, the group is not identical to the vector space that the group acts on. So rotation matrices are separate from the space that they act on. So you can rotate 2-dimensional vectors, but rotation matrices are not 2-dimensional vectors. Okay. Lots of fancy words. Here's another thing that you have to hear. Here's another word that you actually have to know about. It's called a representation. We already talked about matrix representations. So we said the matrix representation of roto translations is like this thing SE2, right? And a representation is, however, more general than that. So matrix representations are just one form of representations of a group. More generally, a representation is a function that takes you from an element of the group to something that acts on a vector space. So for instance, if we take the rotation matrices again, as an example, rotation matrices are only have 1 degree of freedom, right? Which is like in 2D, it's just an angle, right? I can give you an angle, and then you can give me the rotation matrix, as you learned in high school, right? So basically, in the case of rotation matrices, this is an angle, and then there is a function that takes you from that angle to the matrix representation of that that rotation group. So there is a function that takes you from an angle to the corresponding rotation matrix. And for rotation matrices, you learned this in high school, right? It's this cosine theta minus sine theta, that whole shenanigans. The same thing exists for any other group. And the interesting thing is that this function there has a bunch of properties. And you learned that function, for instance, for rotation matrices, just in terms of like, okay, if I need the rotation matrix for this angle, I will just pop in the angle into this rotation matrix, and then I'm done. But actually, there is a literal way to derive for any group this mapping that goes from an element of the group to this matrix. And generally, this mapping is sometimes quite complicated. So far, nothing interesting has happened, other than just throwing around a bunch of fancy math words, as I'm sure you've noticed by the bored expression on your faces. Which is fine. We're moving on. This doesn't matter. I'm wondering how much more will you tolerate before everyone just zones out? Do we need to discuss this? Sure. Okay, I don't need you to understand everything on the slide, but I do need you to just remember this funny notation here. So this funny notation here says that we have a function on some vector space. So in this case, think about images, right? Images are a function defined on R2. So an image is a function that takes you from a 2D coordinate to the color of that 2D coordinate, right? Good. Makes sense? So now we have some group, like some transformation group. Let's say we have a rotation. We have the group of rotations. The group of rotations has an effect on an image, right? It is a perfectly reasonable thing to state, I want to rotate this image by 90 degrees. Makes perfect sense, right? In mathematical, like when we want to formalize this, we say, well, okay, we have the space of functions over R2, which in our case might be like, for instance, images. Then we have our group. So maybe the group might be rotations, or the group might be rotor translations. And now we want to formalize the idea of I take an element of my group and I apply it to my function. So I rotate my image, for instance. And the formalism that people have introduced for that is called. Okay. Oh, okay. Even the projector isn't having it anymore. So so the formalism for this is called a left regular representation. So left regular whatever, but the word representation pops up again, right? Representation again is this idea that there is this function that takes you from an element to the group to something that transforms something, right? And in this case, again, there is just basically a function that takes an element of the group. So it's like L is the representation. It is parameterized by the group element. So for instance, you say, I want to rotate the image by 90 degrees, and then you apply it to your image, which means it takes a function as input, and then it gives you another function as output. So in this case, for instance, rotations might, rotations, you can define a rotation function. It takes an image as input, and then it gives you as output rotated images. But it's good to note that images are themselves functions. You can, of course, parameterize them as samples, as an array. But fundamentally, the image is a function, and the function is defined on R2, right? And so the way, for instance, rotor translations act on images is that they actually transform the coordinates that the image is defined on. So the way you would think about it is you would say, okay, I have an image. I want to rotate the image by 90 degrees. What you actually do mathematically is you take the input to the function, which is a 2D coordinate, right? And then you rotate all the inputs to the function. And then that's how you rotate the image, right? Okay, so the image is rotated, in fact, by taking the input to the function that is defined on R2 and then rotating that input. Does that make sense? Excellent, good. I'm very impressed. Everyone is sticking along. And then notice, right, the same thing applies again, right? We talked about you can chain rotations, for instance, and you can also, there's always the identity element, right? So that all makes sense. The same things always apply. Okay, so like here's now we have gone through all of the different ways of so-called group actions. So a group action, when you read that word in a paper, it is exactly this idea that a transformation acts on some space. So a transformation acts on the space of vectors in 2D. A transformation acts on the space of functions defined on 2D. An action, like a group, can have different actions. One action might be on the group itself. So you can take a translation, like a vector in R2, which itself represents a translation, and you can translate it by applying a translation to that vector. You can take a function defined on R2 and translate it like an image, and you can like shift the input to the image, and then you shift the image around. And then this is the point where we discussed that like sometimes the group is different from the vector space that it transforms. So for instance, for rotation matrices, right, like the group rotates vectors. And so then in the case of rotation matrices, these two are different. In the case of translations, these two are the same. Because in the case of translations, the group elements themselves are 2D vectors. But in the case of rotation matrices, for instance, the group is not a 2D vector. Okay, now finally we have all the vocabulary to actually state formally what it means for a function to be equivariant to a group. Isn't that exciting? Great. We've made so much progress today. So what does it mean for a function to be equivariant? So what we needed all this vocabulary for is because we now have functions such as a neural network. So we say we have a function, and that function takes something as input and outputs something. So phi takes x as input and outputs y. And now the thing that we set out to do is we said we want to set out to make our neural network aware of all of these different kinds of transformations that might appear and that might act on that neural network, right? So now we have the language to express that. For functions that we want to be, what does equivariance mean? Equivariance is the property that we discussed in the example of semantic segmentation masks. Equivariance means that if you have a neural network that takes, for instance, an image and maps it to a depth, for instance, or a semantic segmentation mask, it means that it has to commute with the group, with transformations. Which means if I take the input image and I transform it, in this case, in this case, it's a rotation. So I take the input image, I rotate it, and then I apply my neural network. Then the neural network should give me the same output as if I take my input image, apply the neural network to it, and then rotate the output. Does that make sense? Okay, so this is the notion of equivariance. Good. Okay. So now, how do we build? Now we are like, I gave you one. I feel these slides are done well because they always give you something that you can relate to, and then they dump it down again into like, here's more notation. So now we need to introduce some more notation, but not much. This stuff you should already know. And this is actually really, really cool and really important. So you all know about convolutions and you know about cross correlations. Who here took a signal processing class? So, okay, you took a signal processing class. So has anyone, who hasn't seen this integral before, a convolution integral? Everyone has seen a convolution integral before. Excellent, good. So this is just a good old convolution integral. So what we're doing here is we're taking a kernel k and we're convolving it with a function f, right? And note that both the kernel and the function are actually themselves functions, right? So when we deal with images, we sometimes forget about this because the kernel is just a grid of numbers and the image is just a grid of numbers. But in signal processing, you remember that both of them are actually functions that are defined on a continuous thing, right? So both the image and the kernel, for instance, are a function that is defined on R2. The image is a function that takes an R2 coordinate and maps it to a color. The kernel can be a function that takes a 2D coordinate and maps it to a kernel weight, right? Okay, and we convolve images like this. Usually we say, or like rather cross correlation, it's like not exactly the same as convolution actually, but we'll just dance over it. So usually we say the output of the convolution, so k convolved with f, and you can already see there's a star with R2 at the bottom, which will become important in a moment, evaluated at an output coordinate x equals to this integral, which basically means we take the function at x, and then we flip the kernel, and we shift the kernel around. That's what the x prime does. X prime basically shifts the kernel around, and then we integrate over all of the dot products of the shifted thing, right? Okay, good. That should make sense. Now we're going to rewrite it in a little bit. We're going to rewrite it like this. We're going to say, okay, this is just with all of the seemingly useless notation that we just introduced, we can write the convolution differently. We can say, okay, we're going to say that we can shift the function. Like what we're really doing here is we're shifting this kernel around. We're shifting this kernel by an action of the translation group. We're saying that, okay, I have a translation group. The translation group acts on my function by shifting it around. Okay, and so that's just a different way of writing it. Okay, that all makes sense. So now we can rewrite this as like this. So we can say now, well, yeah, so one thing I left out, like, of course, you know, sorry, I forgot the story of these slides. What's the story of these slides? The story of these slides is that you already know that convolutions are shift equivariant. So the point that I should have asked you is, like, why is it that convolution is shift equivariant in the first place? So convolution already has this property, right? When you convolve an image with a filter, the output of the convolution doesn't change when you shift the image around, as you should know, right? So why is that, actually? And the reason for that is exactly because the way that we are applying this neural network layer is a convolution. So the fact that it's equivariant to shifts is because we are shifting the kernel around over the image. Maybe that's obvious. Makes sense, right? But you can maybe already see where this is going. So what would be your best guess? How do you build a convolutional neural network that is equivariant to rotations? So if the answer for should be easy now, right? Like you have all the, if you have paid attention, it should be easy now. So like if you want to build a neural network, so what did we start out with? We said, okay, we have a fully connected neural network. A fully connected neural network is not shift equivariant, but we already know a neural network that is shift equivariant, which is a convolutional neural network. So now we talked about all this fancy notation, whatever. But now maybe the key insight that you should now have is that the reason why the convolutional neural network is shift equivariant is seemingly because like we're taking like the weights of the neural network and we're shifting it over the image. And there's some more stuff we have to discuss, but that's kind of what's going on. So maybe how do you make a neural network that is rotation equivariant? Aha, good. So intuitively, right? So just like the way we can shift the filter around, and then like right at every position we are applying the weights of the filter. If that leads to a shift equivariant kernel, to a shift equivariant neural network operator, then maybe there's an equivalent of that where instead of shifting the kernel around, we not only shift it around, we also rotate the kernel around. Okay, so it is a little bit more complicated than that, but that is on a very high level intuitively what will be going on. But there's like one more little trick that we have to fix. But other than that, this is kind of the gist of today's lecture. And this is unfortunately only one way of implementing neural networks that are invariant or equivariant to certain translation groups. And it's the most expensive way of doing it. And for some reason, which I don't think is very well understood, for translations, we all agree it's a smart thing to do. But for all the other groups, no one does it, for images at least. And there are reasons for that, but like it's not as obvious. Okay, but like let's just keep that in mind. So somehow the solution of building a rotation equivariant neural network has to seemingly be, instead of just integrating over the translations, we will be integrating over like rotations as well. Okay, good. Okay, so as we just discussed, convolutions are already translation equivariant. Fully connected neural networks are not translation equivariant. But there is a relationship that you can, there is something we will be able to see in just a moment. So let's say we have a fully connected neural network that takes endless digits as input, which is probably something that you guys have implemented in the first deep learning class that you took. You probably implemented the classifier on top of endless digits. So for endless digits, these are small enough, so you can just take the image, you flatten it into a big vector. These are 28 by 28, which yields 784. When you flatten it, and then you just stick it into your fully connected neural network, and then it'll give you a distribution over the class of the digit. So this fully connected neural network, as we know, takes every layer looks like this. It takes like the output of the previous layer, which in the beginning is just the image, right? X0 is just the image. Then it applies a weight matrix, and then it adds a bias, and then it has a nonlinearity. That's every layer of the fully connected neural network, right? So it turns out that convolutions are a special case of fully connected neural networks, and they are related in the following way, which you may or may not know. So in a fully connected neural network, this weight matrix here is just like dense, right? So let's say your neural network had a hidden layer size of like 128. Then the first layer of your fully connected neural network would have a shape 784 by 128, right? It would take like a vector with 784 inputs, and then it would basically generate 128 activations. So this is going to be the weight matrix. In a convolutional neural network, it turns out you can write it in the same way. Namely, in a convolutional neural network, you can write it with a dense weight matrix, and the dense weight matrix will look like this. Have you seen this before? You've seen this before? Who has seen this before? This is called a Toeplitz matrix. So it should be relatively intuitive, right? So because what you can see here is basically W1, W2, W3. These are, in this case, three weights of the kernel. And now what we're intuitively doing is we flattened the image, right, into a long vector. And now we are taking the kernel and we're and it's local, right? So for instance, we are applying it to the upper left-hand corner of the image first, which basically, so this is, unfortunately, this is done for 1D signals because it's, otherwise it would be a little bit complicated. But like imagine the input was a 1D signal. Then we apply it to this first element here. So it's just these three numbers and everywhere else it's 0. So for the rest of the function, it's 0. And then that produces the output at the first location, right? And then we shift the kernel by 1, which basically means we just shift it down. And then the weight matrix looks like this. So it turns out that for convolutions, just by basically constraining the weight matrix to look like this, we gain all of these properties. We gain the property of being shift equivariant just by virtue of constraining the weight matrix to have a particular property. And so in fact, you could try this out. You could now go ahead and on MNIST, you could take the MNIST digits. You could train your fully connected neural network. Then you could take your image after you trained it and you shift it, and it'll break. And then you could go ahead and you could parameterize each weight matrix in your fully connected neural network like that, which is the same as having a convolutional neural network. And then you could train it, and now you shift the digit, and nothing will happen, and everything will still work. Does that make sense? Okay, good. Unfortunately, convolutions are the same is not true for rotations, and we'll tackle that now. So for translations, as I had already said, for translations, the trick seemed to be to like take basically a set of weights and like shift them around with representations of the translation group. Now we'll do the same with rotations. Here's a problem. So images are a little bit weird because an image is a grid of pixels, right? So what have we done in an image? In an image, we have discretized the 2D space that the image is defined on, and then we report a value for each sample of that space, right? For images are special with respect to translations in the following way. Images already sample the space of translations. So because each pixel is a representation of the translation group, right? Each pixel basically is just a 2D location. So shifting the image around just means like shifting the thing around. So in other words, if I have a kernel and I want to basically build a convolution that is shift equivariant, I can take it to the image and I just shift it onto these positions of every pixel. And each position of the pixel is already a representation of the shift group that I'm interested in contrast to the rotation group. What do I mean by that? So my image is defined as a function that takes a 2D coordinate to a color. It's not a function that takes a 2D coordinate plus a rotation angle to a color, right? So, and that's now, unfortunately, the thing that we'll have to talk about for the next little while. But initially, I asked you, right, like how would you build something that is rotation equivariant? And you said the right thing, which is now we're going to be integrating over the angles. It just turns out that integrating over the angles is much harder than integrating over the translations because the translations are already neatly sampled in our grid. The angles are not. The image itself is not yet discretized in the space of rotations. So what we're going to do is we have to first build something. And what we're going to do is we're going to build something that goes from images that are only defined on translations. And it's called a lifting convolution. And what it's going to do is it takes the image's input, which is only defined on translation, on like shifts. And then it's going to basically copy it to the rotation channels. It's basically going to make another copy of the image in the space of rotations. So we already have a representation in the space of translations. Now we're going to make one in the space of rotations. That's the job of the lifting convolution. Okay, whatever. And it shouldn't come as a surprise that the way we're going to do that is we're going to take our kernel, just like earlier we took our kernel and we shifted it around on the image. Now we're going to take our kernel, we shift it around on the image. That is basically the thing that is the translation group thing. And then we'll rotate our kernel and we do it again. And every time we do it, we actually generate a new feature map. So the first time we translate it with the normal kernel, that's going to generate our normal feature map just like in a normal convolutional neural network. Then we're going to rotate our kernel. We do it again. That produces the next feature map. So like for every rotation of the kernel, we'll basically get another feature map. And now the way you can interpret this, right, is like that earlier your image was only defined on x and y. Like the image had a pixel color for every xy coordinate. The output of the lifting convolution will now have a value for every x, y, and for every angle. Because for every angle, you have rotated your kernel around once, and you convolved your image with the kernel again. Does that make sense? Okay. So far, so good. So this is easy. It would be nice if we would be done. There's one unfortunate little trick, which is not entirely intuitive. So this is, yes? Yeah, totally. So the funny thing is that CNN is kind of an overloaded term, because when you say CNN, you usually mean the thing that shifts the kernel around in the image space. So when you say CNN, you usually mean something that is shift equivariant. But it is totally possible to build a neural network that is invariant to invariant, for instance, to rotations, but not to shifts. And the way you can think about it is, in fact, like what would that neural network look like? Maybe it might look like a fully connected neural network. And the fully connected neural network would have the property that if you give it an image as input, it would give you like some output. And now if you took the image and you rotated it, it would still give you the same output. But if you took the image and you translated it, it would give you a different output. And that is totally practical. Let's think about, and it's actually easy to implement. Does anyone know how that would look like in this case? So how would the, yes?
Would the kernel just be the same size as the image, and then you still rotate the kernel?
Exactly. Did you hear that? So yeah. So basically, in this case, the thing that makes it rotation shift equivariant is the fact that you're taking this kernel and you're shifting it over the image. But if the kernel if you would just not do that, then the output would not be indexed by the xy shift anymore. It would only be indexed by the angle. So you take the kernel, you rotate it, dot product with the whole image, rotate the kernel, dot product with the whole image, and every time you get an activation. Does that make sense? Great question. Awesome. Okay, so the big question which should be in your mind now is, okay, so this is the first layer of the neural network. This is always the thing that you have to do in the first layer. And the translations are special because this is kind of already done for you. Your signal is already defined on like shifts. Rotations are like any other group is different because you first have to basically lift it to this space where you have whatever axis you care about. The thing you should ask yourself now is what happens in the next layer. So the first thing that we'll prove is that, or like the first thing we'll show, which I haven't told you yet, is that this first layer has the property that it is in fact shift and rotation equivariant. What does that mean? It means that if you take the input, like this is your input image, and now you apply the convolution that we just discussed about to the image, it'll look like this. So this is x, y, and rotation. And now if you take the input image and you rotate it first, and then you apply it, and then you apply the same lifting convolution that we just discussed, then you will see that the output will be rotated as well. And now there is something else that is, let me see if I can ask the question so that some of you have to answer it instead of me explaining it or like doing a bad job at explaining it. So like maybe I shouldn't have shown you the slide first. So think about for a moment what actually happens when you rotate the input to this convolution that we just discussed. What happens to this output? So just the output, as we just discussed, right? The output is now this volume here. So the output is this volume where you have the xy for each translation, and then you have the rotation that indexes the next axis. What actually happens when you rotate the input? What happens to this volume at the output? Yeah.
It's shifted.
Right. Exactly. So and it's going to rotate it. Yeah. So like there's actually now two things that happen to this output. The output doesn't only rotate. The output also gets like how do you call this? There's an operation in NumPy that actually does it. It like roll. Do you know the NumPy operation roll? NumPy.roll. What it does is it takes an array and it like rolls the whole array down and it pops the last element up onto the top again. So this is exactly what would happen. So if you rotated the input, so if you rotated this image, let's say by 180 degrees, not only would the output rotate, but also depending on how you discretize this, you would have to roll through this array by the same amount. And like now, intuitively, why does that make sense? Intuitively, this makes sense because now, previously, when you just had a single feature map, we said we had a function that was defined on just R2, just on translations. The image was just a function defined on R2. So when you acted by rotation on that function, it just rotated the function, done. So it just rotated the input to that function, right? But now this output here is actually a function that is defined on x, y, and the angle. So now when you apply a rotation, it does rotate the x and y, but the final axis, this red axis here, right, that axis just gets shifted according to that angle. So like, and that's the thing that rolls the thing around. Does that make sense intuitively? And now you have everything you need to know to build the next convolutional neural network layer. So this is now the action. So like now if you take the input and you rotate it, not only does the thing rotate, but also it gets shifted according to like, and the amount of shift is according to however you discretize this group. So if you don't understand this yet, like feel free to ask a question. I'm happy to explain it again. It's any questions on this? Great. Okay, so what happens in the next layer? So brief reminder, we've built the first layer of our neural network, which has the sought after property, which is that it's rotation equivariant. So basically another way of putting it is now that we know exactly what happens when we rotate it. Now for the next layer, it gets a little bit more complicated. But not much. The thing that you kind of have to think about is you have to build a layer again that has the same properties. So it has to be, again be a layer where you're basically like integrating over the angle. So the same thing has to happen again, right? So that is exactly the same that we just did. Before we just took the kernel, right, and we rotated it, and for every time we rotated it, we just applied a copy of the rotated kernel to the image. So let's think a moment we could do exactly the same thing again, and it turns out that is one part of what we have to do. So for the next layer of our convolutional neural network, for every kernel that we want to apply to our image, we're going to take it, apply it to the volume, then we're going to rotate it, and we're going to apply it again. Two things are going on though. The first thing is that now the image has this x and y, and it also has this angle component here. And note that it has this x, y, and it has this angle component. But more so, there's actually one dimension missing here, which is like the feature dimension. So actually, right, you might have, this was just with this was the convolution with one kernel, which means it was, in this case, a black and white image convolved with a black and white kernel. But usually when you do endless classification, right, you convolve your black and white image with lots of kernels in the first layer of your neural network, the number of channels, right? So the same thing happens here. It's just like now if you, in the first layer of your convolutional neural network, want to convolve your image with this kernel, for every channel in the kernel, you'll have to rotate that channel n number of times. So actually the output, if you had more than one channel, the output of this thing would actually now have another dimension, which is the feature dimension. So this is the output for one of these kernels, but you might have channel number of kernels, right? Okay, so that's the first thing to keep in mind. The second thing to keep in mind is that when we build a convolutional kernel now, the convolutional kernel will not only have an extent in the x and y, so it will not only have a footprint in the x and y, it also has to have a footprint in the rotation axis, right? Your convolutional kernel will look just in the same way as the convolutional kernel looks at a neighborhood in the translations. The convolutional kernel will also now look at a neighborhood in the rotations. Does that make sense? Okay, so basically the kernel that you're convolving with this thing here will also be a 3D volume. that's good. And now, when we say we rotate this kernel, basically the final piece that you have to know about is that just in the same way as you have to do this periodic shift to this image when you rotate it, when you rotate the kernel, you have to do the same thing. So what you're going to do is you're going to build a kernel that has x, y, and then it has as many channels as you have, like, discretized the, like, it has an xy footprint, and it has a footprint in the angle dimension. And when you rotate the kernel, you not only have to rotate the kernel, but you also have to apply the same periodic shift that you have to apply to the image when you rotate it. But then, actually, exactly the right thing happens. So this is now, like, let's say now, this is a good image. So let's say now this was our input image. So our input image had these two little smileys, right? So this here was the output of the lifting convolution. So we took the kernel from the lifting convolution, and this output here was just that kernel like shifted, and each of these is like a different shifted kernel, right? And now this is going to be our new kernel. This is going to be the kernel in the second layer. The kernel now has x, y, and it has, again, also the rotation component. And when we apply this convolutional kernel to this volume, we will now shift it in the x and y, and we will shift it in the rotation dimension. And every time we shift it in the rotation dimension, we have to also like roll this rotation dimension around. And then what would we expect? We would expect that if this is our kernel, it should match our image here. It should match our smiley exactly at the corresponding coordinate of the angle dimension, right? So these two smileys are identical up to shift and up to some rotation. So just in the same way, imagine for a moment these two smileys would be rotated the same way. Now if you had a normal kernel that would just be a smiley, what would you expect? In the feature map, in the output of the convolution, you would expect two peaks, which is exactly where the kernel matches the smiley twice, right? And now we almost expect the same thing. It's just that now we also have this rotation dimension. So now we also expect two peaks, but we expect the two peaks to be at exactly these two spots here. One peak at the smiley with this rotation here, and one peak at the smiley with this rotation here. Does that make sense? Questions? Okay, good. Okay, long story short, so now we have built the second part. So we have built the first convolutional neural network layer, which was a special lifting convolution. Now we have built the second layer and actually every other layer after that. So now, in fact, we can put all these layers together and we can train this thing end to end. And it will have the same property as the normal convolutional neural network, which is shift equivariant. It will now also be rotation equivariant, which means that if you have an image like the one that we just looked at, if you have an image like that, now we have a guarantee that if this thing appears twice in your image and one of them is rotated, it'll have exactly the same effect as with shifts. So you can, any part of the image could be rotated, and your convolutional neural network will still do the right thing. Make sense? Yes?
I have a question. So it seems very natural how you would extend this to like scale invariance. You just also scale your filter.
Yeah.
But to me, then it sounds like the cost of doing that grows like very exponentially because you have to do all combinations, right? So, like, is that still computationally feasible to do it for scale, translation, and rotation?
Great. No. So you might ask, okay, so like the answer actually is it depends. So actually, I think we'll kind of, so first of all, thank all of you to be involved in this lecture to the degree to which you are. I promise this will, in your lifetime, this will pop up. Like, just wait for it. Like, right now, you'll be like, why do I care about this? If you do any research related to machine learning, you will care about this in like 5 years from now. In fact, you might already care about it now, but you just might not know. So today, right? Okay, let's just skip the rest of the lecture. I'll spare you some painful detail. Well, okay, so like the rest of the lecture can be summarized as this. You can kind of prove that the functions that we just built are like fully expressive, which means that any function that is, this can parameterize any shift and rotation equivariant function, okay, whatever, which is not true of one other example, maybe briefly about this. So you could be smart and you could tell me the following thing. Well, if I want to build something that is rotation equivariant, one other way of, like, let's say I wanted to build a neural network that's rotation equivariant, there's one really easy way of doing it, which is you take all your filters and you make them rotationally symmetric. So you can take your filter and you make it rotationally symmetric. then you will notice that the same thing holds. You can convolve your image with the filter, and then when you rotate your image, nothing will change. And an example for this is, for instance, this little dot filter here. You can convince yourself that if you no matter how you rotate that input image, the output will always behave that nice way. But why would you not want to do that? Because this neural network is useless. Like, it can't actually make any meaningful predictions. So this is not expressive. Like, there is a whole set of functions that you want to learn that you will not be able to learn with this thing. For instance, if you want to do semantic segmentation, it turns out it's really important to be able to reason about edges. And if you have this filter, that filter can't reason about edges. It can only reason about dots, which is not particularly useful. And I don't know. Yeah. Okay, so that just as a side note, so you can show that this is like as expressive as it gets. So then the question basically that you might ask is, why is no one using this? So the first insight is all of you are using it when you're using convolutional neural networks. But convolutions seem to be special. Like, everyone is using convolutions. No one's building rotation equivariant CNNs. Oh, you dropped your phone, by the way. Or maybe you put it down there on purpose. The reason is exactly the cost. So that's one key reason. So as we just discussed, right, if you have exactly as you said, like, the cost of this grows pretty quickly. So now we want to make our thing rotation and translation equivariant. Okay, translation equivariant, whatever. Rotation, we have to add this whole other dimension to our neural network activations, which is we have to discretize the space of rotations. Previously, we just had to discretize the space of translations. Now we have to discretize the space of rotations. Now let's say we want to build something that is rotation, scale, and translation equivariant. With this group convolution paradigm that we just discussed, exactly as you noticed, you might imagine you have to add one other dimension to your activation volume. And now this puts us in a little bit of a pickle, because I think we all agree that your visual system is equivariant to a whole number of transformations. So for instance, it is equivariant to scale. Right? If I move something back and forth, nothing changes for you. It's equivariant with respect to rotations. If I rotate something, nothing changes, right? It's equivariant to a whole number of other things. Like, in fact, another example, which is like somewhat less intuitive, but it's equivariant to things like color, right? So like, if you take this chair and you for certain transformations of color, like, nothing perceptually changes, or like you would still identify it as the same thing. So your brain is like pretty good at a bunch of these things. So if you wanted to build something that would have all of these guarantees, it's computationally infeasible in vision. There are, however, domains where today this is computationally feasible and very important. And one example for this, is AlphaFold. So who knows about AlphaFold? Okay, you've heard about AlphaFold, I hope. So AlphaFold, just for the record, is a thing that like takes protein sequences as input, just the sequence of protein, and then it predicts how that protein will fold in 3D. Okay, we're not going to talk about AlphaFold, but one of our guest lecturers might be Ellen Zhang, who's a friend of ours who does protein folding at Princeton. So when you build neural networks that act on molecules, then all of the stuff that we discussed today is super important and very, very, very useful. So state-of-the-art algorithms that take molecules as input and predict some properties of molecules, those exploit exactly the kinds of things that we're discussing, and this is in fact what they're being used for today. So for drug discovery, for like making predictions on like small graphs, like it can be summarized whenever you have a small graph and you have a small amount of training data. So now why is that? You all know another way of making a convolutional neural network rotation equivariant. What do you do when you train a convolutional neural network often? You do data augmentations, right? You take your image and you mirror it, you rotate your image, and that turns out has actually the same effect as what we just discussed. So it ends up having the same effect, so you can just like, and you know that this must be true because you're just adding channels. Like all of the stuff that we're doing, right, is just adding channels, and then we have kernels that have these additional channels, and the kernels are just constrained to have certain values in these additional channels. So like the kernel is just the same value and it's just rotated a bunch of times, for instance. And if you just train with like lots of rotations, then your neural network over time will just grind this out. It'll just see an infinite amount of data and it'll just grind it out. The problem is that for some groups, it's actually not possible to do these kinds of annotations. So for instance, for scale, for scale, for instance, like, right, you can take the whole image and you can scale the whole image, no problem. But you can't take a part of the image and scale it. And like then, I mean, you can, I guess. In theory you could, but it wouldn't look very realistic, right? You could like, in theory you could take like a patch of the image and then blow it up and like composite it on top of the image again, but it's not going to look like a real image. So doing data augmentation for some groups is very hard, but for some others it might be very easy. So whenever you have a lot of compute and the group is relatively easy, then data augmentation is the answer. But if there is domains where you don't have a lot of data, or you have a group for which it's very hard to like do data augmentation, then you're kind of stuck. If your graphs are very small, like for instance, like, I don't know, like small molecules, then you're good. Everything you learned today is basically the starting stuff for that. If you want to deal with images, or like with like big signals, videos, images, then status today, we don't know how to do it, which is kind of a problem. So maybe one of you will solve it. But this is actually one of the big questions in vision today. So like, how do we build neural networks that take images as input and then are guaranteed to make the correct predictions? Even though, like, another way of putting it is, right, you want to learn from little data. You don't want to, like, if you were to look at a human child grows up, it doesn't see that much video in its lifetime. And it still has all of these properties of like being equivariant to shift, scale, all of these different things, right? So seemingly, your brain has a mechanism to pick up on these kinds of rules very quickly, and we don't know how that works. But we would like to build things like that. So we would like to build neural networks that take video as input, and from very little video, they discover the rules by which, by which that data is generated. Yes?
So to which extent do people like try to solve this question from like by looking at like brains and neuroscience like?
Let's put it this way: people have been trying, but with very little success. So in fact, the only example of like of an insight from neuroscience that has made it into mainstream machine learning, you all know about, which is convolutions. So one of them, if you read the convolutional neural networks paper from Yann LeCun and the other folks, and actually they in fact cited another paper from like some Japanese dude whose name I unfortunately forgot. That paper, that original one that they cited and that they were inspired by, was a great paper, and the author started with an F. And that paper was motivated by an experiment from the 60s by Huber and Wiesel, which was the experiment where they took a cat, they drilled a little hole in its head, and then they stuck an electrode into the brain of the cat, and then they sedated the cat, and they put it, I'm not suggesting you should do that, obviously, it's like, that seems very cruel, but then what they did is they put the cat in front of the screen, and they fixed the head of the cat, and then they showed it very simple stimuli. They showed it like an edge that is like moving over the visual field of the cat, and they showed that there are neurons in your head that respond to only edges. They basically said, look, here's a neuron in your brain, we can measure it, and it only responds if we have an edge that moves across the field of view with this speed. Okay? And that was one of the motivations for convolutional neural networks. Even though, as we now learned, you can also arrive at convolutional neural networks from a completely different angle, which is just from the angle of like realizing that you're looking for neural networks that are shift equivariant, and then looking at convolutions, and then you could also get there. And in fact, I don't know how much each of these two perspectives. And then actually the way it worked, I think, was that Yann LeCun and these other folks, they were probably just motivated by signal processing, because in signal processing, right, like digital image processing, you all have probably filtered an image before with a filter, with like an edge detector or something like that. So people in image processing, of course, already knew about convolutions for a long time. And so that is another angle at which you could arrive at convolutional neural networks by just saying, oh, filtering works really well. I wonder if you can take filters and build a neural network around it. So it's interesting. You can take these three perspectives at arriving at convolutional neural networks, right? But other than that, there has not been, to the best of my knowledge, any insight from neuroscience that has inspired modern deep learning architectures at all. And people are trying, but I think the problem is that we have very bad imaging systems that can't actually image your brain at high enough resolutions. Like for humans, we can only do MRI, and MRI has like millimeter resolution, and in each cubic millimeter, there's like 1 million neurons, so that doesn't help anyone. You can do EEG, which is incredibly noisy. You can stick electrodes into monkey brains. We do that here at MIT, which is, for one, a little problematic. But for 2 also, like you can't stick 1 million electrodes into a monkey brain. Damn, what is going on? Fun. Right, so yeah, sorry, long story short. So far, yes, people are trying, but we, nothing so far. So there is hope though, so like all of the stuff is not useless that you learned today. So group convolutions, the best way to think about them are like the naive way of doing it. Like that's the first thing you would come up with, and you've noticed that like the motivation is pretty easy, right? You say, okay, we make it shift equivariant by shifting the kernel around. We make it rotation equivariant by rotating the kernel around. It turns out there are smarter ways of doing it, but they're very far from mainstream, and that's an active area of research. So there are almost certainly architectures that have approximate equivariances that are much cheaper than the stuff that we were discussing today. They use the same language, plus much more complicated things. But these things exist and people do research on them. And actually, I did have a few examples for, I've written a paper with stuff like that. So there are papers in 3D reconstruction that exploit these kinds of group convolutions. So for instance, there's papers that do 3D semantic segmentation with 3D rotation equivariant kernels. We wrote a paper on like in robotics, you want to have the property that if you predict grasp locations, you want the grasp locations to, you don't have lots of demonstrations in your robot. So that's a domain where you're constrained on the data set. You can't just like collect a data set of demonstrations with a robot and then ask the human participant to collect the data set 1 million times every time with a rotated mug. You can't really do that. So you would really like that the predictions by your neural network are rotation equivariant, such that the robot doesn't have to see many samples in order to learn how to grasp a mug, for instance. So that is one example where these things are practically useful. So these things exist, but so far not mainstream. Okay, I'm going to let you go for today. Thanks for bearing with me, and see you soon. Bye.